Hi everyone. This next presentation will be given by Michael A. Karls and will be on modeling a diving board.
So thank you. So this is should I start?
Yes, you're good to start.
Okay, thanks. So this is a project that I worked on with Brenda Scocellis when she was a student at Ball State. This was started out as an honors thesis for Brenda. And okay, so the beam equation is a classic fourth order partial differential equation used to describe the transverse displacement of a vibrating beam that one may encounter in an introductory course on boundary value problems or mathematical physics. And a special type of beam that can be modeled with the beam equation is the cantilever, which is a long, thin rectangular bar that has one end clamped and the other end free to move up and down. And so our goal is to address the question, since we can think of a diving board as a cantilever, how well does the beam equation model a diving board? Okay, so we're going to first develop a model for a cantilever beam that's based on the beam equation and includes terms for damping and forcing. And then to verify our model, we're going to compare measured data to our model with Mathematical's manipulate command. And this comparison incorporates all of our investigations into a single case in which the parameters can be varied in real time to study each of our original models. Okay, so let's consider a horizontal beam parallel to the x-axis with clamped left end at x equals 0 and free right end at x equals L. So there's a picture of our diving board, our cantilever beam. And we'll assume the beam is homogeneous with a uniform rectangular cross-section at any point x along the beam. And we'll take the x-axis to be the rotational axis of symmetry of the beam. We'll assume the beam is in rotational equilibrium and suppose that the only forces acting on the beam are vertical and lie in the xy plane. Okay, so any time t and at any point x along the beam, forces acting on the beam will displace the beam vertically by an amount y of xt, deforming the beam's axis of symmetry to form a curve in the xy plane known as the elastic curve. And using Newton's second law and the ideas of bending moment and shearing force, we find that a model for y of xt is given by the following initial value boundary value problem for x between 0 and L and for time t bigger than 0. So here's our setup for our model. Okay, so I'm going to go through and explain what each of these things are in this model here. Okay, so the first equation, that's the beam equation with forcing and damping. That's a partial differential equation. And constant c is related to the beam's modulus of elasticity and moment of inertia. K is a damping coefficient and G controls the forcing. Okay, and then boundary conditions 2 and 3, those tell us that there's zero displacement and zero slope at the clamped left end of the beam. And for the free right end, boundary conditions 4 and 5 indicate there's no bending moment or shear force. And initial displacement and velocity at each point of the beam are given by equations 6 and 7, respectively. Okay, so if you use separation of variables, then you can find a solution to this initial value boundary value problem 1 through 7 is given by this expression here, 8. So we got a function v, which I'll show you in a minute, times this sum. And so here's the v function, and that involves g and c and l. And here's the x sub n's. They involve cosines, sines, hyperbolic cosines, and hyperbolic sines. And mu sub n, that coefficient there, that's related to the constant c and k, and that alpha sub n in there, that's the nth positive root of this equation here, a cosine of alpha L plus hyperbolic secant of alpha L equals 0. Okay, so here's how you find the ANs and BNs. So you find the ANs by integrating the x sub n's against a shifted initial displacement f of x minus v of x. And then the ANs and BNs are related by equation 14 here. So this is how you can solve for the coefficients a sub n and b sub n. And the v of x, that's the steady state solution to this initial value boundary value problem. And solution 8 reduces to the non-damp case or no forcing case if you set the K or G coefficients equal to 0, respectively. Okay, so what we wanted to do is test out this model by performing an experiment. And so here's our, I guess you call it a quote, diving board. We used a 2-meter stick clamped to a table on the left end. And so that's what we use for a physical diving board. And that's Brenda pulling down the diving board on the right end there. And then we marked off 15 tape mark points along the ruler. And then what we did is we filmed this with a video camera and then we analyzed it with, at the time we did this, it was called World in Motion software. That morphed into Tracker. So Tracker used to be called World in Motion software. That's a physics demonstration software that you can use to look at a video of something and then just look at frames and capture points in the video. And we collected vertical displacement data once every 30 seconds as ordered pairs relative to an origin we set at the leftmost tape mark on the beam. Okay, so to compare the actual data to our theoretical model, we need to define our model's parameters and initial conditions. And so we clamped the 2-meter stick to the table, and so the beam had a length of 1.6 meters, and our beam curved slightly downwards with origin at the leftmost tape mark. So an appropriate choice of initial position function is a quadratic polynomial found via a least squares fit. And so what we found is that the initial displacement, a good representation is a of x minus b of x squared, or b a times x minus b times x squared, where these are what a and b turn out to be. And for initial velocity, we just assumed that it was 0 at every point. Okay, so we still need a value for constant c as well as for k and g if we wish to include damping and forcing. And so we started by simplifying our model to one without forcing or damping. So we just let k and g be 0, and we tried to estimate c from its definition in terms of the beam's modulus of elasticity E, moment of inertia I, and mass per unit length of the beam, which is m. And so c is equal to the square root of E times I over m. And the ruler is made of some unknown hardwood with a mass of 0.3014 kilograms, overall length of 2 meters, and a rectangular cross section of width B is 2.625 centimeters and height D is 0.76 centimeters. And hardwoods such as white oak have an elasticity of about 1.2 times 10 to the 10th newtons per square meter. And for a beam with a rectangular cross section of width B and height D, I is given by 1/12 B times D cubed. And so using 17 and 18, a guess for C is about 8.7 square meters per second. Okay, so here's our model again. And so we know the beam's length L, and then we can compute the alpha sub n's numerically. And once the alpha sub n's are known, we can use our choices of C, K, G along with f of x and g of x in 13 and 14 to compute the coefficients A sub n and B sub n for our solution. And so graphically comparing the seventh partial sum of our solution 8 to our initial displacement f of x at time t equals 0, we find that this should be sufficient for our model. And so here's a comparison of our data and our model without damping or forcing. So the red curve is the model, and we're looking at the rightmost tape mark at the free end of the beam. And the blue dots, that's the measured data. And it should be pretty clear that our model isn't really matching the data very well. And oh yeah, due to a time delay in releasing the beam before the camera began filming, we chose time t equals 0 to correspond to the fifth set of recorded data points. But regardless, it should be pretty clear that the model, the red curve, is not matching the data, which is the blue dots. So our choice of C isn't very good at this point. Okay, so what do we do to try to get a better choice of C? Well, we don't really know what type of wood makes up the ruler, so another way to estimate C is to use the fact that with no damping or forcing, the only place that C appears in our model is in the cosine alpha sub n squared CT terms in our solution 8. And so it follows the terms in our model have periods p sub n given by 2 pi over alpha sub n squared c for integers n equals 1, 2, 3, and so forth. And the A1 coefficient, that's the largest coefficient of magnitude in our model, and so we'll have the most influence So we use period P1 to find our second estimate for C. So with alpha 1 is 1.17 and P1 is 16 over 45 seconds. That's the average period of the displacement data at the free end. It follows from 19 that C should be about equal to 12.87 meters squared per second. So we put that into our model. And so now, again, the red curve is our model and the blue dots is our measured data. We don't have forcing or damping, and we're looking at the free end of the beam. It should be pretty clear that the model and data periods match, but our model doesn't attain the same amplitude as the measured data over time. So the amplitude is too high for our model. And unlike our model, the beam's amplitude, if you look at it carefully, it actually decreases slightly over time, which suggests that at least damping and possibly forcing should be incorporated into the model. So if we add in forcing and damping, that increases the complexity of our model. And from 9, we see that C and G appear in the steady state solution V of x, and from 11, it follows that K occurs along with C and the mu sub n coefficients. So we need to find a way to choose values for C, K, and G that takes us into account when computing the A sub n and B sub n coefficients with equations 13 and 14. Okay, so in Mathematica, there's a command called manipulate that you can use. So a method for including every term in our partial sum solution, dynamically estimating all three constants C, K, and G at once is possible. So using manipulate, we construct the model with C, K, and G left as variables that can be changed by means of sliders in real time to see how the model is affected. So that's actually what we're doing in our graph. So you can move those sliders for C, K, and G, and you can watch at how that impacts the red curve and how you can see if the red curve is matching up with the blue dots, which is the data. And the comparison of the model to the actual data is done graphically with values of C, K, and G chosen to get a reasonable graphical fit. And so we kept our C to be 12.87 square meters per second, let G be 0. So we didn't assume forcing at first. We got a better graphical fit with K equals 1.81 meters squared per second, or inverse seconds as seen in our figure 3. But what should be clear is that even though we're including damping in our model, we get a significant improvement, but the measured data values consistently lie below the model values, especially at the beam's right end. So we're always overshooting the data with our model. So to account for this, we introduce forcing to the model by choosing G to be 9.8 meters per second squared and adjusting C or K as needed. And figure 4 shows the beam's displacement over 3 periods at the free end with damping and forcing included in the model. So now we have C is 12.87 meters squared per second, K is 0.94 inverse seconds, and G is 9.8 meters per second squared. And we get a root mean square error between model and measured data of about 1 centimeter. And to me, this is amazing how good this is. And this is so as a check-in to see if we can do any better, we use Mathematica's find minimum command with these initial choices for C and K. So we find numerically that with 12.84 meters squared per second for C and K equals 1.01 inverse seconds, we get essentially the same error as our graphical fit. And this is a graph. Each of the 15 tape marks, we're looking at the blue dots. That's the measured data and comparing it to the red curves, which is our model. And again, I'm amazed at how good this is. It's very pleasing with the result we're getting here. Okay, so using a simple experimental setup, a wooden 2-meter stick clamp tape, digital video camera, and computer software, we have been able to show that the beam equation can be used to model a vibrating cantilever beam. And as often the case in modeling real-world phenomena, we had to revise our initial model to get a model that matches reality. In addition to the experiment outlined, other questions such as the following could be addressed. So would the beam equation model an actual diving board? What about adding in an impulse at the free end to model a person springing off the board? How about other physical systems for which the beam equation with different boundary conditions would be an appropriate model, such as a bridge span with supports at both ends? Or are there other forcing terms that would be more appropriate? For example, how about a forcing term that is a function of the distance from the clamped end? And would such a forcing term work better mathematically? And do forcing terms such as these make sense physically? Okay, so there's a list of our references for this work. And then what I want to do now is I want to go back and actually show you, like, since we have a little bit of time left here, like a derivation that we actually included in this paper for this project for the beam equation, because we actually didn't find such a derivation in any textbook, so we actually included this in our paper. Okay, so to find a differential equation satisfied by y of xt, let's start by looking at the forces on a small piece of beam between x and x plus delta x at time t. And we'll suppose that the only forces on this piece of beam are due to its weight, damping from air resistance, and vertical shear at each end. And to incorporate damping into the beam equation, we can use Stokes's law, which says that for a small sphere traveling slowly through a fluid, such as air, the drag force on the sphere is proportional to the sphere's radius and velocity. And so for simplicity, we're going to assume the damping on a small piece of the beam obeys a law similar to Stokes' law. And so it follows from Newton's second law that the total force on this piece of beam should be equal to the net shear force plus the drag force plus the weight. And so the total force is mass times acceleration. And then we have the net shear force, and then those are the first two terms, and then the drag force is the third term, and then the weight is just the last term. And here m is the mass per unit length of the beam, gamma is a proportionality constant, and g is acceleration due to gravity. And if you divide equation 20 by m times delta x and let delta x go to 0, we get this relationship between y, the vertical shear force, and so we really want as an equation that only involves the displacement y. So to get rid of the v term in 21, we next look at a relationship between vertical shear and bending moment. That was established in 1851 by German engineer J.W. Schwedler for use in his analysis of bridge trusses. So for beams that are in rotational equilibrium, the vertical shear is equal to the derivative of the bending moment with respect to x. If we differentiate 22 with respect to x, it follows that 21 can be written as follows. So now we have a relationship between y, the displacement, and bending moment m. And the final relationship we need to get an equation involving only y of xt comes from the studies of the bending of beams done by Jacob Bernoulli, Leonard Euler, and Charles Louis Navier. It's back in the 17, 1800s. And Bernoulli and Euler observed that at any point along the beam, the bending moment is proportional to the reciprocal of the radius of curvature of the beam's elastic curve, and Navier determined the correct proportionality constant. In particular, the bending moment is equal to E times I times the second derivative with respect to x divided by 1 plus the first derivative of y with respect to x squared, that quantity to the 3/2 power. So here E is the beam material's modulus of elasticity, and I is the moment of inertia. The rectangular cross-section of the beam at x with respect to the horizontal line passing through the center of mass of this cross-section. So this quantity E times A, that's also known as the flexural rigidity. That can be assumed to be a constant due to the uniformity of the beam. If the beam bends only slightly so that the derivative with respect to x is close to 0, then 24 can be approximated by this linear equation, m equals E times I times the second derivative of y with respect to x. If you differentiate 25 twice with respect to x and use the fact that the flexural rigidity is constant, then 23 becomes this expression 26, which now is a relationship only involving the displacement y. And then we replace the quantity square root of v times I over m and gamma over m and 26 with a constant c and k respectively. We arrive at the beam equation with forcing and damping. So that's a nice little derivation of our beam equation. And that'll be a good place to stop.